equations. We're going to touch on the normalization. We're going to look at the RBF kernel. So we are going to look at basically question 3 to 7 as well. But that's a bit later inside of it. It's also all mixed in here. So it is support vector machine. And inside of it, we have the k-means clustering at the very end that I'm also going to touch on and show you how to do it for your assessment. And if there is any adjustments, we will also communicate it with you. Okay. So let's start. Support vector machine. So we're doing learning unit 3, and it's basically, we're doing the support vector machine. It's the linear separation. So we're going to focus on applying support vector machines. We're going to explain the kernels, going to do some dimensional reduction, and then we're going to also apply the bias variance trade-off, or you guys are going to search up on it a bit as well. Okay, so we're going to try and separate the data using a hyperplane, because sometimes the data isn't in a very nice orderly separation. It's in groups and clusters that have some that intermingle and intersect with each other. So that's why we're going to use this. So how does it work? So we're going to classify obesity based on weight. So let's say we have a thin Barbie on the left-hand side and we have a fat Barbie on the right-hand side. Okay, so we have thin Barbie is 50 kilograms and fat Barbie is 150. Okay, so this is basically a obesity data set. So let's go and look at an average. Okay, so if we drew the threshold, so the line that grouped the one together, so if we had the grouping here on the left-hand side, and we had a threshold there, then our middle, our healthy middle weight Barbie, that's not fat and not skinny, is going to say she's not obese, she's upset, she's going to sue us. Okay, so we can't really have the threshold that close to a group. So what are we going to do? So let's see what we can do. If we put it in the middle, it's like she's going the medium of, well, a little off slim is going to be inside of the margin, but it's not quite ideal, because there is some that's going to still fall inside of that margin that's not actually inside of that margin, and or outside of it. So let's actually see what's happening. So what happens if we have a very fit Barbie? So we have a very fit Barbie, and all of the muscle weight means that this Barbie is very healthy, but they classify her as obese. So this is all of the BMI. So BMI rating is usually calculated based on the height of a person and the weight of a person. So it has nothing to do with muscle weight, bone density, how much, a few other factors as well, but those are the two big ones that I can think of. And then the muscle weight would just put you over. Okay, so this muscle Barbie will be overweight, but she's actually quite fit, not necessarily skinny, but she is not obese. Okay, so that is where it is very tough to make a distinction. So this is where we're going to have the bias variance trade-off, and we're going to see what are we going to do, how are we going to fix this scenario. Okay, so we can say this model is trained on the weight, so the BMI is just focusing on the weight and the height, and not how healthy or unhealthy the person eats, because there are people that I see that is like 40 kilograms, 50 kilograms, and they live off of sweets. So that's I don't know if you guys know those people as well, but they have fantastic metabolisms. Well, the rest of the normal people, we just struggle with eating healthy, right? Okay, so this is the bias variance trade-off. So this is when the variance is huge, so there is a huge difference. So we need to go and equal it out. So we're going to use a hyperplane. So in this case, this is where we have our classical data. So our classical graph will show, okay, there's quite some interlaps and overlaps that's going to happen. But if we change the view in what we look at, so instead of looking at the graph, like, okay, there's some, it's askew, there's no linear line there. But if we look at a hyperplane, so if we look at it in more than 2 dimensions, then we're going to get the margin. So margin is the hyperplane that's going to separate it. And we have 2 vectors, support vectors, that's going to help us separate it in a 3D basically model. And I'm going to show you how that works as well. So we're going to have, we're going to split the data. And it's not always easy to split it. So that's why, where is my pretty picture of a hyperplane? I'm quickly going to get it because I thought it was on this side. There we go. There it is. So instead of having the squiggly line on a 2D surface, we're going to look at the 3D feature space. And we can see there is a plane that does make a distinction between the 2 different groups. And that is why we're going to look at that instead of looking at a 2D picture and trying to fit it into 2 groups, because that is very hard to do. It's like it's not always possible to group it like this. So that's why we're looking at the hyperplanes. Okay. So we're going to do it mathematically, and the mathematical formula is basically a half of the distance of the weights. So it's a weight vector. So if you guys remember in your assignment 2, you guys are given a weight vector, and you're going to get the distance, and you're going to divide it by 2. Okay, so you're going to use this formula. Okay, so this is going to be the distance between the 2 support hyperplanes. You guys are given the W, which is your 2 weights, and you're going to calculate this. Okay, so this is your margin, and you're going to calculate this value. Okay, and it's going to help you. So this is the formula that you're going to do. But let's first go and look at the hyperplane. So hyperplane on a 2D line, so it's a maximum margin and a minimum line. So we're going to look at the weight times the x plus the weight of variable 2 times x. So we're going to have the weight of 1. So it's the weight of the x1s. So the x1s is all of the rainfalls in this case, and the x2s are the humidity. And we're going to look at the weight of the humidity and the weight of the rainfall. And then we actually also have a bias. So this calculation has a bias already as well. So we're going to add the bias, and we're going to equal it to 0. So we can also calculate the bias if we are given the weight and the x values. So let's go and see. So definitions of weight is the importance. So it's the importance of that feature in the model's prediction. Okay. Then we're going to also have the bias. It is the offsets that allows the model to shift the prediction to have a better fit. Okay, so a better fit, we want the better fit. Okay, so the bias is going to help us make sure that fit Barbie falls into the healthy category and not into the unhealthy obese category. Okay, so let's see. How are we going to do that? So we have the weights as the strength of the relationship between inputs and outputs. So this one is also like a correlation. It's not it's similar. Okay, so you're going to have weights. So it's the strength of the relationship. So we have, in this case, we have the rainfall, and the outputs, I think in this case, I'm not sure what the output is yet. It's late on. I'm gonna get there. So it is the relationship between the rainfall, and I'm not quite sure what the output is yet, but we're also going to see that later on. And then we have the bias, which is the flexibility. So to fit the data and make sure it doesn't pass through the origin, because we cannot have zero in anything. Okay, because the origin means there's nothing going on. Okay, so let's go and look at the next thing. So, okay, how are they learned? So we are going to start with a basic weight, and we're going to optimize it, and we're going to adjust it as we look at the model building, as we build the model. And we're going to use gradient descent to minimize the loss function. So you start off with, let's say, a weight of 1, which is a very basic weight, and it can be absolutely incorrect. But as we carry on and build and train the model, it actually helps with the gradient descent. We're going to get the ideal weight. So we're adjusting the weights as we go. And then we're going, as we iteratively go over the model, but you guys should will not be doing that. That is in PDAN. So you're going to do it next year. Okay, for those that are busy with PDAN, that is what you should be doing. But we're going to look at gradient descent Tuesday. Thursday. We're going to look at gradient descent Thursday. Okay, so this is the question that you guys got in your formative assessment 2. So this is your assignment 2. You are given a linear support vector machine, and you have a vector with weights 3 and 4. You're going to calculate the margin width. Okay, so we're going to find the norm of length W. So we're going to get the norm of W. So it's going to be the square root of the weights squared added together. Okay, so we have, in this case, it's a square root of 3 squared plus 4 squared. So it's a square root of 9 plus 16. So it's going to be the square root of 25, which is equals to 5. That's nice. We actually have a nice number that is squareable. So we're going to use the formula, and we have the margin is equals to 2 over the norm of W. So we're going to have the margin as 2 over 5, which is 0.4. Okay, so that is similar to what you guys are going to do. You guys are just going to change the values because you have different values that are given to you. Okay, so what other examples do we have of weights? The weights is going to be your formative 1 is 10%, your formative 2, it should be 2, not 3, is going to be 50%, and your summative is 40%. Okay, so let's see here. We have formative 1 is 100, and it's 10%. Formative 3 is 25, which is 50%, and summative is 40, which is which the weight of 40%. So let's see. We have 100 for formative 1, which is 10. We have, if we add all of these together, so 5 plus 4 plus 1 is 100. So let's get what the weight counted. So we're going to have formative 1 is 100 marks that you got. So you have 100%, so you got 10 points. For formative 3, you got 25, but it counts 50%, so it's going to be 12.5. Okay, and then we have 40, so it's 40 out of 40 is going to be 16. And if you add all of these together, you're going to have a 38.5%. So you are going to fail your module since this formative 3 is very important, and it was counted 50% of your marks, but you did bad. So even though you did better in the summative and you did fantastic in your formative 1, since your formative 3 was really bad and your summative wasn't good enough, you've actually failed it. Okay, so that's why you would still fail the model even if that happened. So let's see if we had something else. So we had a formative 1 that did fantastic. You had a formative 3 that was, you had a formative 1 that was very bad. You had a formative 3 that did fantastic, but your summative is below the mark. Okay, so you're going to have your formative 1 is going to count 2.5. You have your formative 3 is 50, but we have requirements. So if you have, so it's 52.5, and you have to at least get 40% in your summative for you to pass the subject, and you got 30. So that is less than 40%. So 40% weight is going to give you 12. Yes, you have passed overall, but you did not pass with more than 40%. So you're still gonna fail. Okay, because this is still very important. Okay, so the summative is so important that even though you did pass it, it's still a fail since this mark is very bad. You could, in this case, get a re-exam or a resubmission for your summative. Okay, so you guys can also go and read up on that. Then I put this one in here. So this is going to be your question 5. Okay, so it's normalization. So we have a data set here, rainfall, humidity, weather, and the label. So it's sunny or rainy. Okay, so that's why rainfall and humidity is important. We're actually predicting if it's raining or it's sunny. Okay, so you're going to see that it's sensitive to the units. So we're going to need to scale data. So rainfall and humidity especially, we need to scale it so that it's between 0 or 1, or otherwise -1 to 1, so that it's scaled. Okay, so how do we scale it? We scale it by using normalization. So we're using normalization to scale it, and we're using the z-scores. Okay, so we're going to standardize the data to have a mean of 0. So we have the average of 0, and then it's going to be between -1 and 1. And we're going to have, this is -3 times sigma, which is your standard deviation. It's three standard deviation places from the mean. So we still accept that. It's still within acceptable range. And the formula is the z-score is equals to the x minus the mu, which is the mean or the average, divided by the standard deviation. So what do we need? We need the mu or the average, the mean, and we need the variance to get the standard deviation. So let's go and calculate it. So we're going to have the data points. You guys also were given data points, 5, 10, 15, and 20. So we're going to calculate the mean. So it is the average. So it's all of them added together, divided by the number of values or data points given. So you have a mean of 12.5. The variance is x minus mu, or the mean, squared, and sorry, it's sum. There is an error in mine. It's the sum of them squared. No. Goodness, it's always hard to draw this. Okay, there we go. Close enough. Okay, so it's the sum of all of the x's minus the average squared over n. Okay, so we're going to get all of the x's, which is given to you. It's given to you at the top. So at the top, you were given the points. Those are your x's minus your mean that you calculated. So you calculated the mean, we can get every single value and we can square it. So you guys can do this in Excel. You don't have to do it on paper or like this. You can do it in Excel. It's a lot easier to do it in Excel. Then you're going to sum it together, add it together to get your variance. And sum of all of the x's, x minus y mean squared. And then you're going to divide it by n, which is 4. We have 4 data points, so it's n4. So we have our variance as 31.25. Okay, and then calculating the standard deviation is easy. We have it, the standard deviation is the square root of the variance. Okay, so we have the standard deviation as 5.59. So we can calculate now x minus mu over standard deviation. So we're going to have x as 20. It's the last point, and we have 20 minus the average over the standard deviation is going to give you an approximation of 1.34. So your z-score is going to be 1.34. Okay, that is going to be your calculation. There was also a class that was given to you guys by Gareth. It was a class on a Saturday, and it's also on this, especially the z-scores, because it shows you where to use your z-score table. Very important to go and look at that. I am just doing the normalization. I'm not doing the z-score part. Okay, so you guys should go and look at that. Okay, so let's see. We have the data of rainfall, humidity, weather, and the label, which is your indication of rain or not rain. And we're going to maximize the margin. So let's go and look at it. Let's go and look at what we can do. So for rainfall, we have the mean. So we're going to calculate, add all of them together, divided by 4. Why? Because we have 4 different data points. So it's going to be 6.95. We get the standard deviation. This is also easy for you guys. You can do it in Excel. You have the function equals to STDEV, which is the standard deviation. You choose the whole column and it will give you your standard deviation. It can also give you your variance and all of the other values you need. Okay, then we can scale the rainfall. So now we can scale the rainfall so that it is centered around a mean of 0. So you can go and do it for each and every value. Okay, and we do the exact same for the humidity. So let's see what happens. So we have rainfall and we have it scaled. So in this case, we have x1 and x2. So we have scaled the rainfall and humidity. The rainfall was then 0 becomes minus 0.95. The humidity of 52 becomes minus 0.74. So this is our scaled data for both of them. And then we can see here that that's also what we already had. And now we can go and use this data. Okay, so we're going to get the weights. So the weights does not really have a value yet. Okay, but we have the labels, we have the scale data. So see, we go here. on this side, we have rewritten the data, and it is scaled, so it was the rainfall and the humidity, and then the labels just stayed the same. So we're going to get the weight of the rainfall plus the bias, smaller or equal to -1, and it's going to also have to be greater than or equals to +1. So it's between -1 and +1. Okay, so let's go and calculate it. So actually, let's go and plot it first. We're going to plot, so it's going to be the temperature. Okay, this is temperature and rainfall, so it's not the humidity, but it's going to have two different vectors or margins, and it's going to tell us where it falls inside of it. So in this case, we have one of the sunny temperatures that is too far inside of the margin. So in this hyperplane, that we're going to have to go and look and see what's happening there, because it might be that in this case, temperature and rainfall, it was a very hot day and there was actually a thunderstorm. Okay, so there was a thunderstorm in the evening, so that meant there was quite a lot of rain. But it doesn't always happen like that. When it rains, the temperature does cool down usually. So we need to go and investigate that. Okay, so let's go and see what we can do. So we're going to get the values. We're going to try and find the weights and the biases to best fit the data. Okay, so we're going to try and draw the hyperplane. But here we have the margin. So your calculations stay the same. So you guys are just going to calculate the margin, and it's going to help you. This is the margin. So this is the margin, and those are the two vectors. Okay, so that is why we also want you guys to at least look at that. We will later on show you also further why you, what you're going to do with it. Okay, but for assignment 2, you just have to calculate the margin. Okay, what are we going to do with it? We're going to actually get we're going to use gradient-based methods to make it cleaner, so we're going to do some gradient descent. Okay, so gradient descent, we are mostly going to focus on that in PDAN, but you guys still need to know what's happening. Okay, so we have the hyperplane, we have a margin, and the classes of the one is at the top and the classes of the one is at the bottom. So make sure that rainy and sunny has a clear distinction. So that's why we have a hyperplane as well, so that we have a 3D model instead of a 2D model where the data overflows and overlaps. Since we can have thunderstorms in the evening when the sun was very high, but that was just looking at the temperature and the rainfall. That wasn't looking at the humidity, right? So we could have had a high humidity for that one spot. So for this one, we could have had a high humidity, and that would mean, yes, there would be rain even though it is quite hot. Okay, so don't look at these values though, because 0 is not a very good oh, it's a standardized temperature. Okay, so the standardized temperature as well. So we made sure that the temperatures falls within a certain amount so that we can make sure that it's inside of our scope. Okay, so it's around the mean of 0. So let's carry on and we're going to look at the rainfall humidity label. We have scaled the data, so we're going to plug it into our 4 points, and we have our calculation. So we have half of the weight of 1 squared plus weight of 2 squared. So we did not put in the weights yet, so they're just given as W1 and W2. And this is the formula that we're going to use for this one. This is to get your bias, okay? And we know it has to be greater than or equals to 1. Okay, And then we're going to look at how it's going to calculate out. Okay, so in this case, we are going to have weight 1 times your rainy, which is x and y. So we have your x's plus weight is going to be the y, which is humidity. So we have x1 as this one has x1 as humidity and x2 as wind speed. So we have the weight of the of humidity plus the weight of the wind speed plus your bias is equals to plus rainy. Okay, so that's how you're going to calculate the constraint. So the points that you're going to rotate around. So this is your constraint. You're going to make sure that there's actual, let's say there's actual humidity for it to be able to rain. And that is 0.2. So the higher the humidity, the more likely it is to rain. And sunny does not mean that it's not humid, but the wind speed in this case in sunny would mean if it is a high wind speed, then it blows the clouds away. So the clouds, then it won't rain. Okay, so that's one indication, and we can also apply it to all scenarios. So in this case, we have the Barbies. So we have that the skinny people have other variables that we have to look at. So we have to look and make sure that the muscle Barbie does not fall into the obese category. Okay, so we have to look at the bone density and also at the muscle weight, because a muscle weighs twice as much as fat. Somewhere I read that, but you guys can go and research that and make sure I'm not lying to you, please. And then we have data points that lie exactly on the margin line. So they are actually very important because there are boundary variables. So they are going to make sure that we actually are it's actually valid. So those boundary variables is going to be important. We want to look at them so that we are making sure that we are actually within our that our data makes sense and the bias and the variance isn't too far out, because it doesn't help we have a big bias and the whole model is skewed. Okay, so it's important to go and look at those points. Okay, so this is then if we calculate it. So in this case, we have the weights that is given to us. We also are given the bias. So we're given the weights and we're given the bias. And we're given all of the points. So you guys do not have a whole data set. So you are just given the weights. So that's why you can just go and calculate the margin. But since we are given the points as well, we can go and calculate it. So for point 1, so we have point 1, data point 1. We're going to have the weight of, so it's minus 1 and brackets. So it's our first weight times our first value plus our second weight and times our second value. So this is going to be our second weight times our second value, and we have our bias. Okay, so we're going to say it's approximately 1.66 and it is greater than 1. Okay, so it's greater than 1 for I. So let's see, point 2. We're going to have, let's go look back. So it's going to be minus 1. So it is sunny. So let's go and look at point 2. We calculate, we put it in. So we have used this we have used these calculations. So this one, very important. So this y I is given here. This is the label, the yi's. Okay, so we have the label as well, so that's why we have the minus 1 in front. Data point 2, so it's minus 1. We have in brackets, so in brackets, this whole thing is in brackets. We have the weight times the data point, the weight of x2 times the data point of 2 plus the bias. Okay, then we're going to have it approximately 2.15. It is definitely greater than 1, so it is sunny. Then we have 0 0.3. So 0 0.3 is label 1, so it's going to be rainy, right? So we predict it to be rainy. So let's see. We are going to have it as plus 1. We're going to have the weights and the biases calculated as 2.91. And it is actually greater than 1. So why is it actually rainy? So there is a problem with this one. Okay, so that one was incorrect. The prediction did not work. And if we look at the 0 0.4 as well, this is also not working, and there is something wrong with our model. Okay, so this means that we have the prediction is not correct. We need to go and recalculate the weights or the bias maybe, because it is skewing our model output. Okay, so we can see it's not very accurate. Our model is not doing well, so we need to actually go and change our weights and our bias, and maybe it will help. Okay, so let's go and see how we can look at it. So this is also, here is your calculation again, and our model sucks. Why? Because it cannot even predict if it's rainy or not. And how are we going to fix this? We're going to optimize it. So we're going to use gradient descent to optimize it. So we're going to have a loss function that's going to help us decrease the bias, and also going to help us get closer to a more accurate model. So we're going to have a function that is very much the same that we have just looked at. We still have the weights, we still have the eyes, and we still have the plus plus the bias. But we're going to regularization. We're going to have a lambda, or you can call it an alpha, whatever you choose, just stick to one value throughout. And we're going to have a loss function, so we're going to recalculate it. So this is going to be going into our loss function. We have a maximum, so it's between 0 and 1, minus yi, so 1 minus yi. So we had yi as plus or minus 1. Then we had it multiplied with a function. So those are our 2 points, plus our lambda divided by 2 and our weights. Okay, so we're going to make sure that we are getting the correct weights in the end. Okay, so we're going to compute the gradients. So let's go and see. We have the weight minus, in this case, n is the learning rate, or it's a squiggly n. And the learning rate is, we usually start at 0.01, and then we calculate it from there. We're going to get the, oh, I forgot what that is called. Okay, I'll remember it later on. Okay, and we're going to calculate it, and we're going to make sure that it is within the margin. Okay, so we're going to make sure that it is either out in the correct side of the margin for case 1 and case 2. So case 1 is going to be greater than 0, so it's bigger than, let's say, if we have this picture, so it has to be bigger than this line, and then case 2 has to be smaller than that line. Okay, for it to work out. Where is my calculation? There we go. Okay, so that is why we're going to look at that. But you guys are not going to compute this too much, but I want you guys to still understand the background of how you're going to do gradient descent, especially in PDAN. Okay, so here we give you the weights, the bias, the lambda, and the learning rate. Yes, thank you very much, Bianca. It's a partial derivative. It is a derivative, correct. Thank you. Like just completely slipped my mind. But luckily you guys don't have to completely know that out of your head, because we have the partial derivative of the loss function over the partial derivative of the weight. We're just going to rewrite it as the lambda of the weight 1. So it's going to be lambda, you're given as 0.1 times the weight. So you are given the L2 regularization. So this we have the L1 regular loss function, and then the second one is the derivative. So it's going to give you the L2 regularization. Okay. Then we're going to compute the function. So the function is the weight plus x, weight of 1 times x1 plus the weight of 2 times x2 plus beta. Okay. And then you can also have the loss condition. So the loss condition you can calculate now, because it's you have been given all of the values. So since 1 minus 0.3595, which was calculated here in this case, there we go, it's that one, which you have calculated here at the top. It's going to violate the margin, and the gradients then is going to be updated, and you're going to do it over until you get a very nice one. So that is why the weights are being adjusted, but you guys are going to do that not manually. You guys aren't going to do that manually. Okay, but all of the steps are here as well. So then you have your weights that you now can adjust, and you have now the learning rate stays the same, but we adjusted some of the weights. Okay, so if we look back, the weight is now just adjusted with the gradient and the L2 regularization, and we have adjusted it. So now we have new weights, and that weight is then used, and we can recalculate it to see if it actually now helps to adjust the variance. And if it does not do that, we can recalculate it again. So this is, you can do this until you get your learning rate, your loss function to be as small as possible. And you can go and see that. We're going to show you how to look at that in PDAN as well. And it's luckily you're not going to do it like this, because this will take ages. Okay, so carrying on. So this is your data. So this is when you have your data scaling. It is your SVM is sensitive, so you're going to scale it, right? Then we're going to do data cleaning. This is for the PDAN students. Please remember to remove your outliers, or if you have kept them, just give us a very good reason. Then we're going to encode our categorical values, because we cannot work with non-numerical values, right? We cannot train a model on categories. So we're going to have yes or no turns into 0 or 1. Okay. So let's go and now look at some extra steps. So this is your RBF. So you're going to have your, I'm going to say, your, okay. This is when you are working with vectors and non-linear SVMs, basically. So non-linear data, we're going to work with our kernels, and we're going to have a Gaussian function. So we are going to have non-linear boundaries. So this is where the 3D model comes in as well. And you're going to have, there we go, radial basis function kernel or a Gaussian kernel. Same thing, it's just a different name, depends on where you use it. Okay, and your value ranges from 0 to 1. So it's very similar to scaling your data, right? But this is non-linear. Okay, so this is non-linear support vector machines. So this is when we don't have linearity anymore. Okay, so previously, before this was still with linear predictions. Now we're going to go outside of the box where stuff isn't linear anymore. Okay, so we're going to use the hyperplanes even more now, since there might also be more than two different groups. Okay, so let's go and look at how we're going to do that. The formula, so this is the mathematical formula. We did in the assignment 2, that square was missing. So it is the exponential value to the power of minus gamma times the absolute value, or the distance, the absolute value of x minus z squared. Okay, so it's the Euclidean distance squared. There we go. So it's the Euclidean distance squared. So the absolute value sign is the Euclidean distance squared. So that is our L2. Okay, so this is our regularization 2 that we're going to look at. And we're going to see how far apart the vectors are from the margin and the inputs. Okay, so we have the distance here. We have the gamma. So it's our scale. And it's going to either dampen or amplify. So the influence. So it's going to have an influence on how far away the points are from our grouping. So we're grouping the data and we're looking at the distance of everything. And then we have the exponent, and it's going to make sure that our results are between 0 and 1. Why? Because we need to make it so that it is easy to read. Okay, so we are given, in this case, we're going to compute the kernel. So we're just going to look at the kernel, and this is the formula of the kernel. So let's go and look at it. We have x as 2 and 2, z as 1 and 1, and we have gamma as 0 and 1. Okay, so this looks a lot like the ones you are given in your assignment 2. So you are going to get your Euclidean distance squared. So you're going to get the x's minus the z's squared and add them together. So you have your Euclidean distance, and we're going to have 2 minus 1 squared plus 2 minus 1 squared is 1 squared plus 1 squared is 2. And why did my calculation go away? Oh no. Okay. My calculation disappeared, which is not ideal. That is not nice. Can I actually paste it back? Can it be pasted back? Oh no. Okay, I'm gonna try and paste it back, guys. Otherwise, it's gonna be horrible handwriting. I wonder if I can just like, can this thing do paste? No, it can't. It can't do paste. No. Okay, I'm gonna try still. I'm gonna try. Okay, so I'm gonna quickly fix it on the normal where I wrote it down, and hopefully we can just close and open this quickly and it will miraculously work. Okay, so let me just fix this. Okay, please work. There you go. Okay, almost there, guys. I shared this on Teams, so I just need to close and open it again on the PowerPoint itself. Okay, so I'm going to stop sharing and then reshare it again. There we go. Okay, then reshare it. And it will probably not pick up where we left off, but we'll quickly go and just hop to it. Okay, we'll just, it just takes a while to load. There we go. Okay. Yay, it's back. Oh, okay. So if you apply it, then you're going to put it back into it. So you have your formula, you have the exponential value to the power of your minus your gamma, which is given. You are have your gamma is 0.1, and it is your Euclidean distance, so it's multiplied by 2. So we have it as exponential value to the power of minus 0.2, and then we can go and rewrite it, and for some reason this, okay, it is approximately 0.818 or 819. So this is your numerical value. Okay, so this is how you guys are going to calculate it. Okay, so that's your kernel. Okay, and then this one is in the wrong place. Okay, why? Okay, I'm also going to show you guys what to do. So this is going to be your grouping. So where's the rest of these? Oh, okay. So I want to do the k-means clustering with you guys, and this is the final summary, but it should have. Why is my stuff broken, guys? Where's my k-means clustering? It's like I put it in here and then it just decided to completely not be there. Okay, let me just, I'm just gonna share my screen with you guys and fix this slide because my k-means clustering that I want to show you guys disappeared with everything else. So let me just get that back quickly. But we still luckily have time. Okay, so give me a few seconds just to get this slides back that just went missing. where's my k-means clustering slides? We have done those. Yes, good. Oh, here we go. Okay, it completely it actually deleted a whole lot of slides, guys. Okay, so let me get I have my slides back now. There we go. Perfect. Okay, so now I can just do a slideshow on mine. Nope. Nope, that's not gonna help. Gonna like save it. Save it twice. Save it twice. Hopefully this time it works. No, it's not going to defeat us. It's just taking a bit more time. So there's a few biases and variances that's not working with us. The computer is biased against my K and N. It doesn't want it. It just wants the SVMs. It doesn't want the K and Ns. Okay, there we go. So I was like, I also left in the beginning of the slide. So let's look at it. So this is going to be your k-means clustering. You are given data points and you are given your centroids. So you're going to give your points. So if we look at the very first slide, you remember that, so we're going to hop back. So we have two groupings and we're going to have a centroid in each of these groupings that's going to be basically the center of that grouping. So that's why we're going to look at the centroid. So that is centroid, center of the grouping. So let's go and see how we can calculate that. Okay, so you are given points, you are given your centroids, and we're going to calculate it now. So you are going to use your Euclidean distance. Fantastic. You're going to use the distance, well, the distance, not the Euclidean distance. You're going to use the distance between each point and the centroid. So let's go and see. This is going to be your point. You have it as X and Y. You can go and put this in Excel, an X column and a Y column. More than welcome. You get the distance to 2.3, so you have the distance to the centroid value. So you have the distance, you're going to calculate it, and we're going to use this formula. So it's going to be the centroid minus the X. So it's the 2 minus 2, and then we have the centroid y minus the y given. So it is 3 minus 3, which is 0. Okay, so this point and this centroid is on top of each other. There's no distance between them. And then we look at each and every point, the distance, and we're going to with this distance, see in which cluster or grouping each point falls in. So we can see, okay, point 1 is very close to centroid 1, so it's definitely centered around C1. We have that point 1 is very far away from centroid 2 or center 2. So we're going to say it is clustered around centroid 1. Point 2, the distance is very close to centroid 1 and very far away from centroid 2, so it's going to be clustered around centroid 1. It's grouped around centroid 1. Point 3 is far away from centroid 1, but it is on top of centroid 2, so we're going to say it is a cluster. It's grouped with centroid 2. Point 4 is far away from group 1, centroid 1. And it is very close to centroid 2, so it's grouped in centroid 2. And that is how you carry on, and all of the points then forms clusters. So we have two groups, okay, two groups around the two centroids. So centroid 1 has point 1, 2, and 5. So 5 is close to centroid 1. And centroid 2 is 3, 4, and 6, because 6 is close to centroid 2. And now we can go and with these points, we're going to use the points and we're going to look at the X values of those points. So for centroid 1, it's P1, 2, and 5. No, give me back my screen, guys. Someone took over my screen. Okay. Then I can go and see. So we have point 1, 2, and 5. So we have X2, X3, and for number 5 it's X2, so I'm going to use that in the formula to get the mean of the X. Okay, so the mean of the X values, so 2 plus 3 plus 2 divided by 3, so it's 2.33. And then we're going to get the mean of the Y values, so it's 0.2, 1, 2, and 5, so it's 3 plus 3, and then 5 is 4. So it's going to be 3 plus 3 plus 4 divided by 3. So it is the mean of 3.333. You guys can also go and say equals in Excel equals to the mean of those 3 points that are around centroid 1. Then you have the new centroid. So your centroid changed from 2 and 3 to 2.333 and 3.333. Okay, and centroid 2, you do exactly the same. You get all of the x's of all 3 points divided by 3. Why? Because we have 3 points, so you get the mean of the x's and the mean of the y's, and it changes to 8.33 and 8, where it was previously 8.8. Okay, so now that you have your new centroid, you're going to recalculate the distance from every point to the new centroid, and you're going to get your new clusters. And in this case, when we recalculated it, our points actually was the same as from iteration 1. Point 1 is still closest to centroid 1. Point 2 is closest to centroid 1. Point 3 is still closest to centroid 2. Point 4 is still closest to centroid 2. Point 5 is still closest to centroid 1. And point 6 is still closest to centroid 2. So that would mean that this clustering from previously is still the same. So we can say that there was no changes in the clustering detected from the first iteration, because this is our iteration 2. Okay, so then it doesn't help to recalculate the centroid because you're just going to get the exact same values that you already have. Okay, so this was your clustering. You clustered around a centroid that's like in the middle of that little cluster, or it is close to it because it's going to be basically the center of your circle. Okay, so you are going to have your clustered around a certain point. Okay, so then it was summarized here as you started with your centroid values. You grouped all of your points in close to these two centroids. You recalculated it by getting the mean, the average of each points, x's and y's, to get your new centroid values. And you did it again. So you made sure that those clusters were exactly the same, and you see the clusters did not change. So it is going to be your final clusters is going to be still stay as cluster 1 is 0.1, 2, and 5, and cluster 2 is 0.3, 4, and 6. Okay, so that is going to be your cluster. So this is actually, yeah, we have done that, and I wanted this one also disappear. Okay, so this is exactly how you do it. So you guys are going to get your points, you're going to get your centroids, you're going to calculate your distance, and the calculations were here. But it disappeared again. So I'm just going to go and get the summary. So we have from point A to the centroid 1, we have a distance of 0. From point B to centroid 1, we have a distance of 1. And from point C to centroid 1, we have a distance of 3.6. Okay, then we're going to look to the distance of centroid 2. So A is the distance of 3.6. B is a distance of 2.8. And then C is a distance of 0. So we can say that A and B is definitely clustered around centroid 1. And point C is clustered around centroid 2. Okay, so now we have a new cluster, so we can now get a new centroid, especially for C1 because there's 2 points. So we're going to add the x's, so 1 plus 2 divided by 2, so we have the mean or the average of the x's is 1.5. And the mean or the average of the y's is 1 plus 1 divided by 2, so it's 1. And the centroid 2 is there's only one value, so we're just going to keep it. So it's 4.3. And then you can go and recalculate it. We have your centroids and to each and every data point. So we're going to have that A and B is still close to centroid 1, and C is still the closest to centroid 2. So we're going to say that the clusters stayed the same. So we have the same grouping as iteration 1. Okay, so that's how you answer that. Then we had to look at the evaluation of a model. So you guys were given the accuracy, precision, and recall. So this is what you need to calculate. You were given a confusion matrix, basically, where you were given the true positive, the false positive, the true negative, and the false negative, and you had to go and calculate the accuracy, which is the true positive plus the true negative. So all of the true values, so it's actually positive and it's predicted as positive and it is positive. The true negative, it's predicted as negative and it is negative, divided by the total. Precision is the true positive, so it's predicted as positive and it is positive, over the true positive and the false positive. So the false positive, it was predicted as a as a positive, but it was actually a negative. The recall is the true positive over the true positive plus the false negative. So false negative is it was predicted to be negative, but it was actually a positive. So in this case, it's it's going to be skewed. So in this case, we want for a medical study, we want the false negative to be as small as possible. Why? Because we rather have false positives than have a patient that is falsely diagnosed as healthy and going home and then having to end up in hospital a few days later. Okay, so that is what we can do. So you guys can also look at it case by case. Okay, so here is a very nice graph that I have made for you guys with all of the actual predicted. Also, you have your all of the precision, recall, F1 score. So F1 score is 2 times the precision multiplied by the recall over the precision plus the recall. And then there's also oh my goodness. Okay, that word. But we're going to focus on the precision, accuracy, recall, and F1 score. And we can't always look at the accuracy itself. Why? Because sometimes these false negatives, the false negatives, is very dangerous, especially in cases of a misdiagnosis. So we rather have it we rather then look at the recall to make sure that the false negatives are as small as possible. Okay. So this is all of the formulas you also need to know. There we go. So true positive occurs when you predict it to be positive and it is positive. So in this case, if you predict the person to be sick based on their symptoms and it is correctly identified. Then you have true negative. Occurs when is negative. So in this case, the person is predicted or identified as healthy, and you look at their blood work and you see, okay, they are healthy. A false positive. So this is a type 1 error. So the model predicts a positive. So we have that the person is sick, but the person is actually not sick. So maybe they have an allergy instead of, let's say, well, actually, that's not, neither of them are good. Okay, so I can't, a false alarm. Let's say it's a false alarm. I can't at this specific moment think of a scenario. But help me think of one, guys. Okay. Then we have a false negative. So a false negative. This is a very this is the one we really do not want. So this one is we predicted that the person is not sick, but the person has a high pain tolerance and does not realize there is he has a kidney stone. Okay, so very bad. We'd actually want to treat it before it gets worse. So that is a missed case. Not very good. So we'd rather have this person taken up in the hospital and looked at. So now I have one for false positive. So this, let's say this person um, has a very low pain tolerance and they have a very severe, they think they are dying and they are categorized as sick, and in the end it was maybe very this is very not that great. Any case, they wanted just to fart. Okay, so that was one thing that could happen if you have a very bad stomach ache and you have a very low pain tolerance. That could happen. Okay, not the best topic, so let's carry on, guys. Okay, so we have the accuracy, which is not always going to help us because it's misleading. So it's yes, it's nice to look at proportional, but it's not always going to be the best one to look at, especially when we're looking at a model. So we'd rather sometimes look at the recall, especially in cases, let's say, cancer screening. We'd rather pick up people that are, we'd rather screen people that are not sick. So it's the false positive. So it's the false positive. We'd rather pick up people that is not sick and say to them, okay, you are not sick, than miss the people that are really sick, that has a high pain tolerance, and that uh, is only picked up too late, and then they're already at stage 4 or worse. Okay, so that's why recall and sensitivity in this case is very important. For precision in this, we can also see spam detection. So we can see that it's vital for the false positives are high. Okay, so for spam detection, the false positives, so we can retrain those, and we can also make it accurate, make it more accurate as we go along. And then the F1 score is actually the overall best score to look at for either case, because it's going to be a mixture of the precision and recall score. So it is going to be a balanced metric, especially for uneven classes. So most of the data sets you guys work with, the cancer data sets, well, the cancer data sets, the classification data sets, usually you have one class that has a very big grouping. So we have like cancer data set, we have a big group of non-cancerous people, so benign cancer, and we have a small group of malignant cancer. So that is going to skew our model. So we can't really just look at our accuracy. This F1 score is going to be more balanced, especially since the classes are not evenly distributed. And if you want, you can also go and um, balance it back out. Okay, but we'll show you guys how to do that in PDAN. So this is not what you're going to look at. So you are going to calculate. I've given you guys all of the formulas for the accuracy, precision, recall. The recall one is just one back. So you're going to get the accuracy, precision, and recall for the um, two that are given to you, and you're going to calculate it, and then you're going to say, okay, so the accuracy of the two is quite equal. The precision of the logistic regression is better, but the recall of the neural networks is better. So we're going to have neural networks is better at recalling. So it's a better catch for diagnostic scenarios. So this is diagnostics, so medical scenarios. But if we looked at our spam detection, then we would have gone with a higher precision. Okay, so with then we would have gone with the precision for the logistic regression is better, so we'd rather go with that model. Okay, So this is close to what you guys are going to do. So you are given a neural network and a logistic regression, but in this case, we're going to look at a decision tree and naive Bayes model. So you are given the true positive, false negative, true positive, false negative, false positive, and true negative for each of the two values. You can go and rewrite it into a confusion matrix if you want to. Otherwise, you can just calculate the accuracy, precision, and recall for both. So let's go and calculate it. Here is your formulas as well. There we go. I've given it to you. So decision tree, the accuracy is 88%. The precision is 44%, and the recall is 80%. For the naive Bayes, it is accuracy of 69.6%, the precision of 24%, but the recall of 96%. So in this case, we can see, okay, the accuracy of the decision tree is better. The precision is better, but the recall of the naive Bayes is fantastic. So we're going to go with the naive Bayes model is better. In medical screening, the recall is prioritized because missing a sick patient, a false negative, is far more dangerous than having a false alarm. So having a patient that is healthy but has to go for a screening. Okay, so that is how you guys are going to also discuss and explain how you guys are going to make sure that it is correct. Okay, so that is the end of what I have for you guys. All of this is doable on Excel. I just did it um, in writing, basically. So you can also do it in Word, but I would like you guys to go and do it in Excel. It's actually a lot easier also to do it in Excel and get all of your calculations nice and in order. Okay, the conclusions and the discussions, you are more than welcome to also add it to Excel. Just number it correctly, please, because we can't always see some of the numbers, so please go and number it correctly. We do look for it, but sometimes we do not find it. And also, if you submit your Excel document, do not change it to a PDF. Please do not change it to a PDF. Just submit an Excel, because if you save it as a PDF and submit it, it distorts everything, and then we can't find the answers. So yeah, that is the advice I have for you. Are you guys still okay? You guys are not freaked out? Okay, Bianca first.
Nadia, I just want to quickly ask something regarding the two questions that's going to change. Um, are the values of the
Yes.
questions going to change?
It's probably just going to be the values. It's not going to be the total equation, total rewrites. It's probably just going to be the values that change. But they will also tell you, and we are also fighting them to get an extension so that you guys can have time to go and do that those few questions over.
Okay, cool. So if we're already done, we'll have to redo.
Those
Um,
questions, yeah.
The,
Yes.
no, I think they have already shared the how the question is going to look like already. Just I think they needed to send some addendum that needs to be sent to us, and then the extension after all, if I
Yes.
remember very well. Yeah. So
Yes.
I don't think
So
that the numbers are going to change. It's just an additional question on the question that is already been asked.
Yeah.
That's my understanding.
Yeah. They
okay.
shared the addendum. It's on the SharePoint.
Okay,
Okay,
perfect. So it should be on the SharePoint as well as in an announcement in Arc. So yeah. Susan, you also
But
had a
the
question.
but the
Oh,
closing
wait.
date has not changed. So
We're fighting. We're fighting for you guys.
okay.
Serena is hard at work fighting for you guys to get that extended. For us as well. We only have so much time to mark.
No need to fight, just change the date.
No, we have to change. We have to fight for it, so we can't just change the date, because we're not allowed to change the date. Okay, Susan.
Hi, Nadia. I just want to find out with question 2 of the logistic regression, because I'm a little confused on the instructions. Are we basically redoing the question even though you guys provided us with the Excel sheet?
Yes, you are going
So
to redo that one. Yes, on your own Excel sheet, and you have to type over the numbers.
okay, so then the Excel sheet is just like a guide of what our final answer is supposed to look like.
Yes.
And then I wanted to find out on the announcement that you guys said you could have to submit separate documents. But then since you're now saying we can do our questions in Excel, it's not possible for us to just submit separate sheets of each question in
You
Excel.
can, yes, you can do that.
Okay. All right. Thank you.
Okay. I will share these slides on Arc with you guys. I don't think I can paste it in here because last time I did that, it did not work. No, I can't paste it here. I will share it with you. Okay, yes, I can't see your name. Sorry.